So I'm here to introduce Tom Oppenheim, Dr. Tom Oppenheim from the Mechanical Engineering Department. He's been at Cal Maritime since 2015. He got his PhD in mechanical engineering from Cambridge and then did postdoc work at the Swiss Institute of Technology. So he's going to talk to us today about his research. It's really interesting to me because it's an interdisciplinary team. And we spent some time talking about what does that mean to have people with very deep expertise from very different disciplines talk to each other with their different vocabularies, maybe some different assumptions about research and data, et cetera. So he's going to tell us about some really cool work that he's been working on. So without further ado, thank you, Tom.
Yeah, thanks, Michelle, and thanks for coming to my talk. So yeah, my name is Tom Oppenheim, and I teach in the Mechanical Engineering Department. For the past few years, I've been working with a lab at the University of California, San Francisco, the Ganguly Lab. And the focus of the research of their lab is to improve rehabilitation protocols for stroke patients. So when a person suffers a stroke, a common issue is that they will lose motor skill in one of their limbs. So it makes life really difficult. The quality of life for them is really impaired. So we aim to develop better rehabilitation protocols for such patients. So before I talk about that, I just want to give a little background about how I got into this research. So I'll talk about some of the work that I did in graduate school and my postdoc, and then I'll jump into what I'm doing with UCSF and how that all ties together. And then I'll just give a brief discussion of future projects that we have planned in the subsequent years ahead. So when I was a graduate student at Cambridge, my PhD was funded by Nokia, actually, and they were interested in developing a new type of cell phone, one that is stretchable, flexible, and they were really big on the whole nanotechnology thing. And at the time, I was working with protein nanofibers that had interesting multifunctional properties. They had interesting chemical, mechanical, and electrical properties, optical properties. Like you could covalently attach conductive nanoparticles to their surfaces and make nanowires. We scaled these nanofibers up to thin films, and ultimately I tried to scale this up to a macroscopic material for applications like this cell phone. They had interesting birefringence properties, and we did other things with this material. So this isn't medically related, but this is how I got started. So a similar side project that I got into at Cambridge was using a process called electrospinning. This was really popular in the field at the time. So electrospinning is basically a process similar to 3D printing, where instead of extruding a melted plastic, you dissolve a plastic in a solvent. We used water, and then you just push that through a metallic syringe needle. And if you apply a high voltage of 1 to 20 kilovolts across the syringe needle on a grounded substrate, you can form this continuous fiber that comes out. And these fibers had diameters of 200 nanometers. So well, there's no students here, so you're a student. We all know what a nano is, 10 to the minus 9th meters. And they can be as thick a diameter as about a few micrometers. And so I came up with a process of patterning these fibers. So if you move this substrate, if you place a substrate just basically a few millimeters underneath the syringe needle, and then you move it at really high velocity, you can actually pattern the fibers if you pre-program the movement of the substrate. So I was able to create these patterns, and we ended up embedding. I worked with a colleague who helped me embed conductive nanomaterials. We used carbon nanotubes inside these polymer solutions, and then we extruded them, and we were able to show that they were conductive. And they happen to be of the same size. So if you look at this image here, the same size as different cell types, and neuron cells in particular had similar sizes to this. And so at the time, there was a huge push to use such materials for tissue engineering applications, or to stimulate neurons, or to pattern them on substrates and then grow them for tissue engineering applications. So from this work, my advisor ended up getting a tenure track position in Switzerland, and she needed some help starting her lab. So she asked me if I was willing to come to this university in Switzerland, which is on Lake Geneva, and I said no problem. So I just helped her start up her lab for a year. I was already familiar with a lot of the things that she was doing, so I helped her out. So this lab is, the PI's name was Stephanie LaCour, and this is the LSBI lab, the Laboratory for Soft Bioelectronic Interfaces. And the focus of her research was on stretchable and flexible electronics. So I'll explain this rat in just a second. So I see all of you looking over there. But she had discovered some time ago, around the time that I was there, that if you basically evaporate gold on elastomeric substrates, or basically materials that are rubber, stretchable, you can, and if you stretch those materials, they'll still maintain their conductivity up to a certain % mechanical strain. So hence, stretchable, flexible electronics. And she was interested in embedding these materials for neuroprosthetic applications. So at the time that I was there was another PI or professor that we worked with, Gregoire Courtine, who had discovered that if you implant similar neuroprosthetic devices into rats with damaged nerves, you can actually make the paralyzed rat walk again. So I think I show a YouTube link. If you go to that YouTube link, you could see the rat initially paralyzed walk again. And I know that at the time they were doing clinical trials with humans. So that was the focus of her research. I built this instrument to characterize the electrical and mechanical properties of her films, thin films. And so then fast forward, the neuroscience community is pretty small, so she basically got me involved with a lab at UCSF, similar type of research, the Ganguly lab. And the focus of their research is improving rehabilitation protocols for stroke patients. So the first thing that they want to do is they want to be able to accurately track or quantify the movements of the kinematics of the upper limb for stroke patients. And then two, once we're able to do that, is to develop better rehabilitation protocols for those stroke patients. So here I have a video of one of our patients. And they're doing the standardized test that I'll talk about shortly, where she will be trying to lift this cup filled with water and pour it into this cup here. And you'll see how much struggle there is. I'll just fast forward to the part where she's trying to lift the cup. So it's very difficult for the patient to move their arm. And so we want to be able to track very accurately the movements of the hand, the shoulder, elbow, wrist, as the patient does this, so we could see if there are patterns in stroke patient movement, so that if there are clear patterns, then we could develop better rehabilitation protocols. So in the last 2 years, I've also had the pleasure of working with several undergraduate students. One of them, I think all of you remember, is Daniel Newmeyer and Kalen Shorger. They graduated last year. Here, Kalen is actually presenting his research he did over the summer at the annual Cal State CSU PERB Biotechnology Conference in Southern California. And this past summer, I also worked with a recent grad of Stanford who helped me with a lot of the clinical stuff. So the lab is always wanting to bring on undergraduate research. They encourage it. It's good for their lab, too. So again, my job has been to develop a system that can accurately track the kinematics of the upper limb, of the shoulder joint, the elbow joint, wrist joint, and of the individual fingers. And so if you think of each of these joints as a ball joint, so I give a little schematic in SolidWorks of a ball joint, each joint can rotate about 3 axes. So here I have little animations of how a joint can move. It can yaw, so it moves side to side. It can pitch, it can move up and down, and it can roll. Okay, so we want to be able to track all of those angles for each joint. And also for the hand. So the doctors, they use specific terminology for specific finger movements. So if you bend your finger, the doctors call that flexion. And if you move your thumb away from your palm, that's called abduction. And if you move your thumb away from your palm this way, that's called extension. And so we want to track the bend angles and flexion of the MCP, PIP, DIP joints. I'm not going to pronounce those words. We need to do that accurately to 1 degree of bend angle. So once we've developed a system that can accurately do that, we then want to bring in stroke patients into clinical trials and have them perform these standardized tests that neurologists have them do. And basically, these standardized tests are called the ARAT tests, or the Action Research Arm Tests. And so basically they'll be required to grasp an object like a cricket ball or a cup filled with water and pour it into another cup, or they'll be required to pinch an object. So this is the pinching, like a marble. And they'll move it from this surface here to a Petri dish over there. And we want to be able to track those movements and see if we can find any similarities in stroke patient movement. So I just have, So I just have a little animation of what we want the patient to do with each of those objects. Okay, so here is one of our patients doing a pinching task. Okay, and again, this is for the ARAT test. So this patient is going to be trying to pinch the marble and then lift it up to this Petri dish here. And so you can see how little control they have of their hand. So it's also been shown that if patients do these tasks repetitively, so if they do this 3 different times, they can actually show improvement in their timing and in their motor skill. And so we want to be able to capture what specifically is doing that. Okay, so there's actually different sensored systems that you can use that can do this. There's optical fibers that have fiber Bragg gratings in them that can do shape sensing. So this is I looked into this initially and it's very expensive. There's very cheap inertial measuring units. So if you guys came to the undergraduate research talk, you saw you present that. So these are like $30. There's camera tracking, which would be the most ideal because the patient wouldn't have to wear a glove. But there are certain issues with that related to our patients, which I'll talk about later. And then there's electromagnetic systems, which have sensors that have very small profile and can track not only the bend angles, but also the absolute position of an object. We ended up using the 2 on the right. So one of the major issues of our patients, some of the severely affected stroke patients, is that their hands after they suffer a stroke are clasped like this. And so I said initially that ideally we could use this optical, the camera tracking system. But when the patient has a clasped hand like this and it's on the table, the camera is not going to be able to track those finger digits. So we have to use some sort of gloved system, censored system. And so I just list some constraints that this glove needs to have. It has to be ergonomic, and it has to be easy to put on. So if you think of a stroke patient having a clasped hand like this, the glove has to slide over that hand, and it has to be easy to put on and not cause any pain. But when the doctors sometimes when the doctors try and pry open this hand, it can be painful. So that's one of the biggest issues in the design of this glove. And then obviously once the glove is on, it has to be accurate. Has to track accurately the fingers and the upper limb. And we were initially interested in making these gloves affordable, like less than $500. And we were thinking of sending these glove systems to the patient's home as opposed to bringing them into the clinic. Because when the patients come in, they spend about 4 to 8 hours in this chair, and they do that ARAT test just repeatedly. So why not just have them do that in the comfort of their own home? And so there's also glove systems that exist on the market that you could purchase, but they either have varying degrees of accuracy or they're just really uncomfortable for the patient to wear. There's also these inexpensive camera tracking systems, Leap Motion. I don't know if any of you have heard of this. But again, if the patient has a clasped hand or even just a curled hand like this, it doesn't accurately track these finger joints. So initially, I did work with inertial measuring units, so the same thing that Carson's using for his work. And so these have lengths of about 1 inch and about 0.8 inches in width. And if you think, and my finger has about a width of about 1/2 inch. So these sensors would have this footprint over my finger. So they're pretty bulky. They're lightweight and they're cheap, but they're bulky. So a couple summers ago with the CSU PERB grant that we got, Daniel Newmeyer and then eventually Kaylin Shorger helped create this system using Arduinos and 3D printing basically mounts on the arm to capture the kinematics of the upper limb and the fingers. And it turns out these were pretty accurate, but they're really bulky. So this is like a good first test, a first good prototype. But the doctor that we were working with, we have a resident neurologist that works with all the patients, pretty much said no. So we have to change something. And that was a common theme, and still is, for this lab. So we tried to redesign this sensor using ELCAD. And so we tried to reduce the footprint. So we took out a lot of the components, the unnecessary components of this breakout board. We reduced the size of it. We added flexible cable. And this had a much smaller footprint than the breakout boards we bought from Adafruit. But one of the big issues with working with humans is that if you have exposed electronics and you do these tests, they don't like it, and understandably so. So we couldn't use this design, even though it still accurately tracked the kinematics of the fingers. So we ended up settling on using an electromagnetic system where this box here emits a magnetic field, and these are the sensors, okay, that track the position and the angles of an object. And they have a very small footprint, so they're about 7 millimeters in length and I think like 2 millimeters in diameter. And they're attached to flexible cable, so they're pretty easy to put on a patient, no wires exposed. But it's a pretty expensive system. So the next phase of this project was prototyping a glove, a censored glove. And so here's a final result of what we got. And it doesn't look like the prettiest thing ever, but this glove is actually pretty easy to put on. And I highlight the word Makerspace because a lot of what we did is things that our students could do when we have our Makerspace facility here. So there's lots of sewing. We had a lot of textile purchasing and altering. There's stretchable fabrics here. We had to cut some of the fingers here. We made 100 different iterations of this glove. We were doing lots of gluing with heat shrink tubing to permanently fix these sensors in them. So that was a big bulk of the work that we did. And so once the doctor was finally happy with that design, so then it came time to animate and model the limb in real time. So two benefits of doing that is the doctors can get real-time feedback during one of these clinical trials, and so can the patient. So it's been shown that patients that do these tests, if they have kind of almost like a video game that they're playing as they do these tests, it helps improve their motor skill. So I modeled the finger, like a joint from here, the MCP to the PIP as a cylinder. And then if you connect 3 of these cylinders together, I recreate the finger. So here I have an animation of it. So this is Jenny grabbing a cube, and on the left you see a video camera of it, footage, and then on the right you see the animation. So we did a lot of verification, the accuracy of all this. She's doing a pinching task, grabbing a cup. So these are all things that the patient would have to do in these ARAT trials. Right, so here, this is the actual test that a patient had to do in the ARAT. So we're tracking not only just the palm and the fingers, but also the wrist, the elbow joint, the shoulder joint. Here's a close-up animation of the hand. And here's a top view image of position tracking of the palm as it does the different tasks. So right now we've collected data from 7 patients, and we want to collect data from at least 10 before we write anything up. And so one of the analyses that we're trying to do is create heat maps. So we're trying to track the position of the index and thumb finger digits as they move through space. So in one of the tests, unfortunately I did not create an animation with a marble, but in one of the tests, they're tasked to grab a marble from here and then move it over to the Petri dish here. So here's a kind of a heat map or position tracking trajectory of the hand movement, just to show how it works. And then here we have a result of the difference between a healthy patient and a stroke patient. So on the left, this is my hand grabbing the marble and then moving it to the Petri dish. So you see kind of a more linear trajectory. And on the right, you see the trajectory that of a stroke patient. So there's lots of shaking. They may have dropped the marble, yeah, I mean, a lot of shaking. And we do similar heat maps for the fingers. So this is one for the thumb. If you think of the thumb as like a straight linkage, and if you could theoretically move the thumb in all possible directions, flex it, abduct it, extend it, you would create this sphere. And so here's a recreation of this movement in a heat map. So this is where we're at in our research. So we have collected data from 7 patients, and the next phase is to see if there's lots of similarities in the movements of a lot of these stroke patients. And then if we find that, then we could develop better rehabilitation protocols for the stroke patients. And one of the future directions that I just thought it'd be cool to show this image is to, instead of putting on a glove on the stroke patient, there's lots of research being done, again with stretchable electronics, where you can put these like water, I think they're called the water tattoos or e-skins on the surface of a skin that have embedded electronics in them. So John Rogers is like huge in this field. So if you could just imagine embedding like finger tracking or arm tracking electronics, these IMUs, in these thin films and just stick them on the hand and track the movements of patients that way. That's a future direction. And that's it. So if you guys have any questions.